this is basically a design problem, and in this design problem we are asked to design a wideband FM using an indirect Armstrong method with only doublers. So doublers, as I mentioned, is that you can only have multipliers, right? These devices in the order of twos, something like 2 raised to power n, right? 2 4 6 2 4 8 16 32 64 128 and so on, right? So since it's an indirect method, so what we have is we have a narrowband FM modulator, and with narrowband FM modulator we have its frequency deviation delta f1, which is 5 hertz, and we have its carrier frequency, which is 20 kilohertz, right? So this is something that is given to us, right? And we know that the bandwidth of the message signal is simply 5 kilohertz. Another thing that is given to us is uh, the parameters of the output of a modulator or the wideband FM modulator, and these includes again the carrier frequency that is desired at 90, and that is 97.3 megahertz, whereas the frequency deviation that is desired is 10.24 kilohertz. So we are given with this information the bandwidth of the message signal, right, the deviation and the carrier frequency at the output of narrowband FM and at the output of the whole thing, that is for the wideband FM, and we are asked to design all of this. This is something that we will take up now. So as a first step, what we are going to do is we are going to validate the problem, and the validation is in terms of whether the claim that the output over here is a narrowband FM and whether over here we have a wideband FM. So we'll do the validation for that. And for the purpose of a validation, what we can do is we can detect what is the modulation index at each. So we know that the modulation index, that is beta, this is equal to the frequency deviation over here, it would be delta f1 by the bandwidth of the message signal, and so this is simply 5 hertz by 5 kilohertz, and that is simply 0.001, right? So it says that if beta is less than 0.3, or if it is much less than 1, then it is a prime example of narrowband FM. So this is check. So over here we have narrowband FM, and the bandwidth is simply by Carson's rule we have bandwidth that is equivalent to 2 BWM beta plus 1, right? And beta over here is only 0.001, so this added with 1 would actually be very similar to 1, and then our bandwidth can be approximated to 2 bm, right? So as mentioned previously, if it is narrowband FM, then the bandwidth is equal to 2 bm, twice the bandwidth of the message signal. So the first is checked. Now moving on towards the wideband, we can do the similar procedure over here as well, and for that what we can, again we can find the beta over here, the modulation index, and that is equal to now delta f2 by bandwidth of the message signal, and this is equal to 10.24 kilo divided by 5 kilohertz, right? And this would be equal to 2.05, right? So this is again another check that it is greater than 0.3. So this is an example of wideband FM, and the bandwidth is easy to calculate. Again, we would have 2 bandwidth of message beta plus 1. Beta is 2.05, so 2.05 plus 1 will become 3.05, and if you multiply it with 2 it would become 6.1 bm, and again the bm is 5, right? So let me just approximate it to uh, 30 kilohertz, right? So over here we would have 30 kilohertz at the wideband FM, whereas in narrowband FM originally it was simply 10 kilohertz. So there is a threefold increase in the bandwidth, right? So next in line is the design of the rest of the parameters, right? So for that, the first thing that we would do is we would try to factor in the number of multipliers that we would need, and by that what I mean is that we know what is the carrier frequency at the output of wideband FM, and we know what is the carrier frequency FC at the output of narrowband FM. So based on this given information we can estimate what sort of multipliers there would be, right? And then there are two ways to go about it. In the first method you use the carrier frequency, that is simply FC2, this frequency FC2 at the output of WBFM or wideband FM. You divide it by the output of narrowband FM, that is 97.3 megahertz divided by 20 kilohertz, right? So whatever is this, that will be the total multipliers, right? So if you divide these two, so they are going to give you M1 and M2, which is over here, M1 and M2, right? So this is one technique, but you know that in multipliers we are also going to multiply delta F1 with M1, right? And then again whatever the output would be over here, then that would again be multiplied by another multiplier. So we would have delta F2, which would be equal to M2 times M1 times delta F1. Remember, delta F1 is multiplied by multipliers, but at the same time this frequency shifter does not change it. It has no role to play, right? So if we do the analysis based on the carrier frequency, that is FC2 by FC1, so we will be stuck in terms of frequency deviation. So if we multiply, that is as I mentioned, delta F2, which is equal to M1 M2 delta F1. So if we multiply this delta F1 M1 M2, we might not get this deviation if we originally select the carrier frequencies FC2 and FC1. So this is the reason that we do not go by this approach. In fact, what we do is we have also the frequency deviation. So what we do is the frequency deviation at the output of wideband FM, we divide this frequency deviation by the frequency deviation delta F1 at the output of narrowband FM. So once we divide that, we will find multipliers M1 and M2, right? Note that in this scenario we can achieve FC2 from FC1 from the multipliers as well as in combination with the frequency shifter, or by use of the local oscillator over here, right? So this is actually the approach that we need. So the division has to be in terms of frequency deviation, because frequency shifter does not play any role in it, right? So this is our second method, that is second approach, which is the correct approach. That is, you divide the frequency deviation at the wideband FM by the frequency deviation at the output of narrowband FM to achieve M1 times M2, right? So if you divide 97.3 if you divide 10.24 kilohertz with 5 kilohertz, so approximately you would have 2048, and that is in terms of 2 raised to power 11, right? So why do we have written 2 to the power 11? This is because it's in terms of doublers, right? We need to find multipliers in terms of 2 as given in the constraint or in this question, that we can only use doublers, right? So this doublers can be in the shape of uh, 2 power n1 and 2 power n2. So whatever over here is, it will be multiplied by 2 power some integer n1, and you will have an output over here. Similarly, whatever over here is, that will be multiplied by 2 power n2, and then you will achieve these parameters that which are already given to us, right? The second thing is, since we know that the multiplication m1 and m2 is equal to 2 power 11, so what we can estimate is that the m1 is 2 power n1 as I mentioned, and m2 is 2 power n2. So we can say that the combination of this n1 2 power n1 times 2 power n2, so that will be equal to 2 power n1 plus n2. So this states that uh, n1 plus n2 should be equal to 11 as mentioned here, right? So n1 plus n2 should be equal to 11. So this becomes our second equation. So next in line is some of the analysis in terms of FC3. So we have FC3 over here. So this FC3 is nothing but FC1, which is 20 kilohertz multiplied by 2N1, right? So this will be our FC3. And similarly, we have FC2 here, the center frequency C2, that would be equal to FC4, whatever would be here, multiplied by 2 raised to power n2. So these are the two expressions which I have mentioned here. FC3 is equal to 2 power n1, the first multiplier, times the output of the carrier frequency at the output of narrowband FM, and similarly FC2, which is the output of wideband FM, is equal to 2 power n2. This is the multiplier, the second multiplier, multiplied by the output of the local oscillator over here, right? So this justifies our first four expressions, right? The next thing in line is, what would be the local oscillator, right? How can we find the local oscillator? So for that, there are several ways to look into it. It says that to find the local oscillator frequency in the frequency shifter, we have the following options. The first option is, you have FC3 and then you subtract FLO, that is the frequency of the local oscillator. So that is FC3 minus frequency of the local oscillator, FLO. So that is one option. The other option is FLO, frequency of the local oscillator, minus FC3. That is the second option. And the third option is FC3 plus FLO, right? So FC3 minus FLO, FLO minus FC3, and FC3 plus FLO. So these are the three options that we can consider in designing the local oscillator. So these are mentioned over here, and we would look into each of these next, right? So the first one is, as I mentioned, FC4 is equal to FC3 minus FLO. So this says that FC4, which is over here, that is equal to FC3 minus FLO. Okay, so for that, this is expressed over here, right? So this says that we can revisit this whole problem uh, from the end, from the wideband FM, and which says that our carrier frequency at the output of narrowband FM, so this is equal to 2 power n2, or the second multiplier. This is multiplied by all of these blocks, right? The second multiplier is multiplied by all of this. So this is expressed over here. 2 and 2 is multiplied by rest of the blocks. And what are the rest of the blocks? The rest of the blocks are, we have FC1, and that is multiplied by 2n1, right? So we'll have 2n1 times FC1, 2 power n1 times FC1, and remember there was a minus sign for the local oscillator, so we would have minus FLO for this. So this whole block is multiplied with the preceding blocks, right? So from this we already know the carrier frequency at the output of narrowband FM. This is given or stated in the question itself, right? We know that if you open this expression, you would have 2n2, 2n1, and you can combine n1 and n2, which I have done over here, n1 plus n2, right? And similarly this 2n2 would go over here. So if you simplify, we know this, which is 97.3 megahertz. We know n1 plus n2, which is 11, done previously over here in the second expression, right? So we know that this is 2 raised to power 11. Also we know the carrier frequency at the output of narrowband FM, which is 20 kilohertz, right? And then we don't know about n2. We need to find n2, so that would retain its shape. We don't have a numerical value for it, and then we are unsure of what is the local oscillator, right? So all of this is available. So from here what we can do is we can extract out the frequency of the local oscillator, which I have done over here, that is FLO, which is equal to 2 minus n2. So if you just solve these expression, the n2 will go on the other side and you will get minus n2. So 2 raised to power minus n2, and then this whole thing will be converging to 4.096 into 10 raised to power 7, and then you can subtract FC2 from it, that is 9.73 into 10 raised to power 7. So you can observe that this number is smaller than this number, so overall this whole thing would be negative. So if this whole thing is negative, that means the frequency is negative, and that is not a solution. So the first option, you can reject that. We cannot work further, as the local oscillator is giving us a negative value, right? So next we move on towards the second option, that is the local oscillator minus the FC3. Again the same procedure, that you would have a local oscillator minus FC3. So you know that 2 and 2 is multiplied by everything. So 2 and 2 would multiplied with the local oscillator, and then there will be a minus sign, and then 2 and 2 would multiply with 2 and 1, and then it will be multiplied with the carrier frequency FC1, which is 20 kilohertz, right? So this is done over here. So 2 and 2 FLO minus 2 n1 plus n2, the output of the narrowband FM, the carrier frequency of the narrowband FM. We know the value of this one, FC2, that is the output of narrowband FM, and we know the value of this, which is 2 raised to power 11, and we know the carrier frequency at the output of narrowband FM. So you simplify this and you will eventually get 13.826 into 10 raised to power 7, and this n2 would be appearing over here in terms of minus n2, right? So in the question it is stated that the local oscillator should be in the range of 400 kilohertz to 500 kilohertz, right? So I have reiterated it over here. It should, the FLO should be in the range of 400 kilohertz to 500 kilohertz. So the possible choices are that you set this n2 over here to be 8. So if you set n2 equal to 8, what you have is, if you simplify this expression by setting n2 equal to 8, then that would be actually giving you 540 kilohertz, which is beyond our permissible range, that is 400 to 500 kilohertz. So n2 cannot be 8. Thus we need to reduce this. So to reduce this we would increase the value of n2, and if we increase the value of n2 we can increase from 8 to 9, and if we set n2 equal to 9, so we would have this whole thing appearing as 270 kilohertz, which is below 400 kilohertz, right? So for the integer value of 8 it is going beyond 500 kilohertz, and for integer value of 9 it is going below 400 kilohertz. So again this option is not valid for us. So we'll go on towards the third option, which is FC3 plus FLO, right? That is FC3 plus FLO, frequency of the local oscillator, over here again, and instead of minus right now we have a plus here. You simplify this expression. Once you simplify it, so the local oscillator can be expressed in terms of 2 raised to power minus n2, 5.634 into 10 raised to power 7. Again I have reiterated the permissible range of the local oscillator, which is between 400 to 500 kilohertz. So simply if we set n2 equal to 7, the local oscillator is actually around 440 kilohertz, which is within this permissible range, right? So you would have to test 6, 7, 8, 9, right? So eventually you will reach this point that would identify the local oscillator range, which is within the permissible limit. So once you reach that value, that is n2 equal to 7, so from 2 you can get n1 equal to 4. That is, remember we said that uh, n1 plus n2 is equal to 11, which was coming from over here. So the combination of this and this, the overall number of multipliers is 11. So if this is equal to 7, right, so that means this would be equal to 4, right? So the first multiplier m1, so this would be actually equal to 2 power 4, and that is 16, and over here what we would have is 2 power 7, and that would be equal to 128, right? So from here what we can say is, if you divide FC2 by 128, you will get a value of FC4, and that value is 760 kilohertz, right? And this value is also your center frequency. Okay. Also, if you divide this by 128, so this is going to give you delta F4, and whatever that value is, that would be appearing over here, right? And also at FC3 these three values would be same. Remember, this value would not be changed because of the frequency shifter, since the deviation is not changed by frequency shifter. So this value, the value of bandwidth, which I have put a sign here, this, and FC4 delta F4 would be same, right? So with this we have concluded all the blocks. So simply you multiply, you can fill in all the rest of the data. It's a very simple process, so I would not do it here right now. But you just, what you have to do is both of these you multiplied with 16 and you would achieve delta F3 and FC3, right? L naught is 440 kilohertz, right? And the bandwidth, as I mentioned, is simply delta F3, and so on. You can fill in rest of the blocks. So I have mentioned some key points over here in the end of this problem. It's a very comprehensive problem. Sometimes in the design problem they give you flexibility. They would say you might be asked that you have the availability of doublers as well as triplers. That is, you could have 2 raised to power n, or you could have 3 raised to power n, right? So with this I will conclude my lecture. The references that I have used is mentioned over here. Thank you very much.